In this video, I will show you how to use the physics principles we learned from Physics 1, Newton's second law, and energy conservation to work with ideal springs. Now, in this example, I will use more energy than Newton's second law, but it will give you, it will still give you an idea of how to get started there. So what I have here is a mass, and I know that the mass is half a kilogram. I have a spring, the spring constant, an ideal spring. The spring constant is 10 newtons per meters. This is the wall, and this is, let's say, the floor. And what I have started doing here is I've started drawing the system schema. Now, I will give you a quick introduction to this tool in case you're not familiar. What I'm doing here, I've started listing the objects in the problem. The first one is the mass, the other one is the spring, and then I'm also including the earth. Now what I'm gonna do, now that I have the objects, I'm gonna show the interactions between the objects. So the mass is in contact with the spring, and this is a double-headed arrow with the character C to indicate the contact interaction between the mass and the spring. Now, the mass is also in contact with the earth, so I'm gonna do the same thing between those two objects. And I know that there is a gravitational interaction between the mass and the earth. That's why I have the lowercase g, character G. Now, I want to remind you, the spring, I consider that I have an ideal spring. And with this model, we mean that the mass of the spring is very, very small. If the spring has very, very small mass, it also means that the gravitational interaction between the two is tiny or negligible. That's why I'm not showing it here. If you have a heavy spring, one that you cannot really claim it's an ideal, then you do have to take into account the gravitational interaction. But this does not happen in introductory physics classes. Now, I've done the system schema. Now I will move on and work with the force diagram. Now I will show you the force diagram if I assume I'm working with Newton's second law. In that case, as the system, I will use just the mass, okay, for Newton's second law. And then the force diagram would look the following. For the system being the mass, I can see that I have three interactions. So I need to show three forces. The one from the earth, so three forces, one pointing down, one pointing up, and the one from the spring. I'm assuming that my spring is compressed, so it's pushing the mass. Okay, this is the gravitational force from the earth on the mass. This is the contact force from the earth on the mass, and this is the contact force from the spring on the mass. Okay, so every interaction has its corresponding force here on the force diagram. The interactions and the system schema in general is a step towards doing a correct force diagram so that you can move on with the correct application of Newton's second law. Now, I don't need to move forward with Newton's second law here, so I'm gonna stop. But at least if you need Newton's second law in your problem, this is how you will be doing it. You will be choosing the system to be just the mass, and then you're gonna use the system schema to do the force diagram. Now, what I want to do here is use energy conservation, and in those cases, when I want to use energy conservation, I will say that the system is everything. And if I assume that the system is everything, there are no forces acting on my system because there is nothing in the surroundings. Okay, so the surroundings The surroundings, when the system is everything, is nothing. There is nothing in the surroundings if you make your system to be everything. Now, all right, so to start with energy conservation, I will write the energy principle. The change in the energy of the system is equal to the external work done plus Q. Now, when we apply energy conservation, we have to choose the initial and the final state. And this is because you can see you have the change in the energy. When you talk about change, you need to have a set initial and final state. Okay, if you don't know what those two states are, obviously you cannot find a change. So let's define those here. The states are. Now, in this problem, what I'm doing, I am compressing the spring. So I'm pushing the mass to the left, I'm compressing the spring, and then I'm letting it go. What I want to do is, I know that by how much I'm compressing the spring, what I want to find out is what is the speed of the mass when the spring is neither stretched nor relaxed, when the spring is at its equilibrium position. So I'm gonna choose as my initial state, let's do this, initial is when the spring is compressed and the final is when the spring is neither compressed nor stretched, let's say at S equals 0. Okay, S equals 0, I'm indicating that the spring has its equilibrium length. It's neither stretched nor compressed. That's the most abbreviated way I can think of to write neither stretched nor compressed. Now, I am moving on with energy conservation, and as we know, as we've done in the past, the first step is to break the energy of the system into the fundamental types of energy. So we have rest, delta ER for the system, kinetic, delta EK for the system, and potential, the change in the potential energy of the system. This is equal to the right side, which includes heat and external work done. Now, because the system is everything and the surroundings include nothing, of course, there is no work done, and we don't have any temperature changes or thermal energy transfer, so the right side is 0. Okay, Q heat is 0 because there is no thermal energy transfer between the surroundings and the system. And the reason why the external work done is 0 is because there is nothing externally of the system. The surroundings include nothing, and nothing cannot do any work on the system. So W external is 0. Now, these are the three fundamental types of energy. R for rest, K for kinetic, P for potential. Now, as I have mentioned several times in Physics 1, rest energy, okay, how would I include the expression here? The equation for the rest energy is mc squared. Now, the rest energy will change when the mass changes. C is a constant, speed of light, 3 times 10 to the 8 meters per second. Now, the rest energy will change when the mass of the object changes. This happens typically in nuclear reactions, and we don't have anything like that here, as we did in Physics 1. So you can say the mass of the system does not change, so the change in the rest energy needs to be 0. Okay, that's how I can get rid of that term. Now, next step, I will break the system into its components, the parts that it includes. The system for energy conservation, the system includes everything. So, for kinetic energy, I will have the change in the kinetic energy of the mass plus the change in the kinetic energy of the Earth plus the change in the kinetic energy of the spring. Okay, I want to remind you, kinetic energy is about motion. My system includes 3 objects, and in general, each one of those 3 can move. So, delta EK of the system becomes the change in the kinetic energy of the mass, the Earth, and the spring. Now, I want to remind you, I did assume that the spring is ideal. And an ideal spring means that it has very little mass. We know that kinetic energy depends on the mass, 1/2 mv squared. And since the mass of the spring is tiny, this allows me to say that this is 0. That's why I can get rid of this term. Now, while this phenomenon takes place, I'm compressing the spring and letting the mass go, and then the mass moves to the right. While this phenomenon takes place, of course, the Earth is moving. I can make the assumption that the speed of the Earth during this phenomenon does not change significantly. So that allows me to get rid of this term. The only thing that I have left is the change in the kinetic energy of the mass that is moving. Now, for potential energy, we know that potential energy is about interactions, and in particular, conservative interactions. Non-conservative interactions like friction do not have any defined potential energy. That's why we calculate typically the work from friction. In this problem, I don't have any friction. The conservative interactions that I have here are the gravitational between the mass and the Earth, and also there is one between the mass and the spring. So I'm gonna have, because I have these 2 conservative interactions, I will have 2 potential energy terms. The gravitational potential energy between the mass and the Earth, and the contact potential energy between the mass and the spring. And then this is going to be equal to 0. Now, I have here the change in the kinetic energy of the mass, and change means final minus initial. So, I'm gonna do let's erase this MF. EK of the mass final minus EK of the mass initial. Okay, the change became final minus initial. The same thing, I'm gonna do the same thing here. EP of mass Earth, this is gravitational final, minus EP potential energy gravitational mass Earth initial, plus the same thing for the spring mass, EP contact mass spring final minus EP mass spring, this is the initial, somewhat tough to write over here. Okay, this is the initial, and then I'm closing that, and equal to 0. Now I can use the expressions that I have for all of these. I do want to use something that I know to make my life easier. When I compress the spring, and I release the mass, at the beginning, in the initial state, the spring is compressed and the mass is not moving. The speed of the mass in the initial state is 0, and because the kinetic energy depends on the speed, this allows me to make this quantity to be 0. Alright, so I have 1/2 the mass, the final speed of the mass, v squared final, that's the final, that's the one I'm looking for, the speed of the mass in the final state, plus mgy final, this is the gravitational potential energy of the mass, minus mgy initial, this is the gravitational potential energy of the mass in the initial state. Now, before I move on, I want to mention something here. I can see the mass is moving at a horizontal on a horizontal plane, on a horizontal line. That means the height of the height of the mass is the same in the initial and the final state. Now here I am using y initial and y final, and I haven't defined those. So how about I say I'm gonna make the origin of the coordinate system to be in my initial state. This is my x initial, and this is my x, and that's the y. Okay, that's my coordinate system, and the origin is at the location of the mass in the initial state. As I was saying before, the height, the y initial and y final of the mass is the same because the mass is just moving left and right. Okay. Now, even if I don't know what is y initial and y final, I do know that they are the same, which means they're gonna cancel out, which is great. I have less terms to think about. Now I have the final potential energy of the mass spring, 1/2 k s squared final, and this minus the same thing in the initial state, 1/2 k s initial squared, and all of this is equal to 0. Now I want to mention something here. I mentioned the final state is when the spring is neither compressed nor stretched, which means I have s equals 0. So this is true in the final state, and if I plug in a 0 for s final, it makes the whole thing, the whole term, to go to 0. So what I have left is only two terms, 1/2 m v squared final minus 1/2 k s initial squared is equal to 0. Now, as I said before, what I'm looking for is the final speed. So I need to solve for v. Now I'm running out of space, so I can add. Let's add one more blackboard. I'm gonna repeat what I had: 1/2 m v final squared minus 1/2 k s initial squared. And since I have 1/2 on both terms, I can get rid of that, and this means my v final is k s initial squared divided by the mass, and since I have squared on the speed, I need to take the square root, so it's going to be s initial times the square root of k over m. Now I forgot what numbers I had, so let's go back. S initial was minus 0.2 and 0.5 and 10. And there you go. I should have been more careful before when I did this, and I'm gonna show you why. I should have used the absolute value. So since I have S initial to be minus 0. No, I think it was 0.2. So that was minus 0.2 meters. So because S initial is a negative number, right? If you take the square of the negative number, you're gonna get rid of the minus sign. So you're gonna have a positive number, and then you take the square root, and that will give you with that's gonna leave you with 0.2 meters. Now that means when you take the square root of S initial squared, at the end what you really will get is the absolute value of S initial, and this will help you get rid of the minus sign. Anyway, if this is confusing, just do the calculations before you take S initial out. So what I have here is 0.2 meters, and the square root, if I remember correctly, that was 10 newtons per meter, and that was 0.5, and I found that to be 0.89 meters per second. Okay, so this is the speed when the spring is neither stretched nor compressed. Now when I go back to my initial to my figure, I want to show you here. So this is the S initial, and when the mass, okay, this would be my final. So let's say the final state is when the mass is here. Okay, this is the mass, this is the final state, this here is the initial state. The spring is compressed. In this state, the spring is in its relaxed length, neither stretched nor compressed. So as I'm letting the mass go with the compressed spring from here and a speed of 0, when it reaches the final state, it will have a speed of 0.89 meters per second. Now, I want to mention, I want to give you a quick summary of the problem and tell you how things will be different in other problems. I started with the figure, and don't forget to do the coordinate system at the beginning. I am listing here the quantities that I know from the problem, and I did the system schema where I show the objects and the interactions. For Newton's, if you have to use Newton's second law, then you will have to use as your system to be just the mass, and using the system schema and the mass, you will do the force diagram. Now for energy conservation, you will be typically in most cases, you will be choosing the system to be everything, and this allows you to make the system scheme, the force diagram, to be nothing. There are no forces acting on your system. Now, energy conservation, delta E of the system equals work external plus Q. And from there, I broke the energy of the system into the fundamental types of energy: rest, kinetic, potential. And then on the next step, I said for kinetic energy, I need to break the system into its parts, and my system was everything. So I have the mass, earth, and spring, 3 terms. This is the part that can be confusing. The kinetic energy is about motion, and every part of the system can have its own motion. That's why I have 3 parts, 3 terms for kinetic energy. Potential energy depends on the interactions, and in particular on the conservative interactions, and that depends on how many conservative interactions you have. For this system, I have 2, that's why I have 2 terms. And from there on, I plugged in, I used the expressions for every kind of energy, and at the end I did the calculations. Now, how can this change? If your spring is not horizontal, but it's vertical, then yes, y final and y initial will not be the same. Okay, in that in those cases where y final and y initial are not the same, you have to be careful because you have to include those in your calculations. That would make the problem a little bit more complicated, but not that much more complicated. But other than that, everything else, all the other steps for approaching springs and masses, they are the same. This is the approach.